Hello, stats students. Welcome back for section 7.2, more confidence intervals. So in section 7.1, we talked about creating or constructing confidence intervals. And I know I pointed out a couple times during the notes that in section 7.1, we knew our population standard deviation. I need to make sure that I point out that we do not know our population standard deviation. Sometimes we don't have that information. So this is when we don't know, but we will know our sample standard deviation, our S. So most of the time sigma is unknown, so we use our sample standard deviation S. When S is used and the sample size is small, remember how we talked about large sample sizes, critical values greater, so our critical value is our Z value, our critical values greater than the values for Z of alpha over 2 are used in our confidence intervals in order to keep the interval at our given level, at our 95% confidence. So these values are taken from the T distribution. So instead of using a Z table, we are going to use a T table when sigma is unknown. So it's really similar, it's just that we don't know sigma, or we've got a small sample size. So here's our assumptions. In order to use our T distribution, I keep saying it over and over again, it's kind of the well-kept or poorly kept secret, is that we must have random samples, simple random samples. That's where we're going to get our S, our sample standard deviation from. And we've got a couple options. We know our population is normally distributed, right? Or we don't know our sigma, or we've got a small sample size. So we look for those things when we do the problems. If I say in a problem, oh, well, S is equal to 2.85, automatically you're going to say, I don't know sigma, I know S, I'm going to use the T distribution. So let's talk for a minute about the T distribution and what it looks like. So I've got this picture up here, and doesn't the T distribution look a whole lot like our Z, right? Our population distribution, or our population symmetric curve. So our T distribution is still bell-shaped. Notice the dark line on my curve here is my Z curve. That's what we've been using up until now. And these dotted blue lines are T curves. And they say T for DF equals 20 and DF equals 5. Let's talk about that in a minute. But it is a bell shape. That bell shape has to be symmetric about the mean. So just like whenever I draw these things, I always put mu right here. Mu is in the center. In addition to being symmetric about the mean is the center of the universe. The mean, median, and mode are all in the center. They're all equal to 0 in our normal distribution. So all of that is the same. The curve approaches but never touches the x-axis on the two ends, the tails, right? It gets closer and closer and closer as we move out more and more standard deviations. It approaches but never touches the x-axis. In a perfect world, we wouldn't have outliers, but we do, and so that's how we keep those in mind. The standard deviation is greater than 1. We can't have a negative standard deviation, right? So standard deviation is still greater than 1. This is a family of curves based on degrees of freedom. So degrees of freedom is a new term. We haven't talked about that, so give me a minute and we will. But notice DF is equal to 20 is a little bit taller and narrower than DF is equal to 5. So it's based on degrees of freedom. And last but not least, remember how in the last slide I said our sample size is less than 30. Well, as our sample size increases, as our N increases, our T distribution gets closer and closer to our standard normal distribution. So here I've got degrees of freedom equals 5. Degrees of freedom are based on sample size. So as my degrees of freedom increase, notice it gets closer to that dark Z curve, the line, not the dotted. So a lot of similarities. There is a ton of similarities. You're going to find that section 7.2 feels just like section 7.1, except we're getting our critical value, our t value, instead of our z value. So degrees of freedom. I've mentioned this now a couple times. It's the number of values that are free to vary after your sample statistic has been computed. Because it's a sample and because it's a small sample, we could have some variation. So degrees of freedom, df, is equal to n minus 1. So sample size minus 1. So we have to have one static value. The other, we could have some variation because it's such a small sample. That's really what the true problem is, and we don't have any population information like mu or our standard deviation. So degrees of freedom are going to be crucial as we find our t values. So critical values, we call it t of alpha over 2. T of alpha over 2. We just did z of alpha over 2, right? So that's all the same. The table is a little bit different. So we can find these. You're going to need to go in the back of your book. In our book, it's Appendix A, Table F. I believe it's right after our z table. Notice down the first column is df, degrees of freedom. And we said degrees of freedom was equal to n minus 1, right? So if I have a sample size of 20, I'm going to go to 19 for my degrees of freedom. You have to remember to subtract that 1. And then you're going to focus over here on confidence intervals. Don't worry quite yet about the one-tailed alpha or the two-tailed alpha, but we're just going to go ahead and use our confidence interval. So everything's going to feel the same except for how we get that critical value to put into our margin of error formula. So let's do a quick example. Find the t of alpha over 2 for a 95% confidence interval. The sample size is 25. So if my sample size is 25, my degree of freedom is equal to 24, right? It's always subtract 1. So I'm going to go over here. These numbers are hard for me to see. I'm going to go to 24 right here. And I'm going to go across to a confidence interval of 95%. So this column. So it looks to me like my t of alpha over 2 for a 95% confidence interval is a 2.064. That is the number that I'm going to use in my confidence interval when I construct it. Find the t of alpha over 2 value for a 99% confidence interval for a sample size of 8. So let's see, sample size is 8. Whoops. So that means degrees of freedom is equal to 7. So I'm going to go over to my table. I'm going to go across my degree of freedom 7, and I'm going to go all the way across to 99%. I'm pretty sure I have that hiding back there, but I can't see it, so let me see what I wrote down. I've got that would be a 3.499 for my critical value. I'm pretty sure this is the first time that I've called them critical values. The t value or the z value is called the critical value. That's what we use as we construct our confidence intervals. All right, so hopefully you're finding that table and knowing how to use that, because we're going to need that as we find our formula for constructing a confidence interval for the mean, so for mu, when sigma is unknown. So again, we don't know the population standard deviation, or we've got a small sample size less than 30. Here's the formula. Again, don't be intimidated by this. Notice in the middle, I've got mu, right? Same setup as what we had before. I'm going to highlight my margin of error formula. Let's see make sure I can do one that you can see, okay? Here's my margin of error formula. So I'm going to plus and minus, x bar plus and minus, the t of alpha over 2 value times s over the square root of n. Please notice that this is really the same formula that we did when we constructed when the sigma was known. We used a z value instead of t. We're using s instead of sigma, but it's still standard deviation, and it's still divided by the square root of n. So x minus that margin of error is less than mu, which is less than x bar plus that margin of error. And don't forget to use degrees of freedom. You will get the wrong answer because you'll put the wrong critical value in for your math. So I know it's long, but I'm hoping everybody's going to tell me that it feels really the same as what we did previously. So let's do an example. So dance company students. A survey given to 10 students found the average amount of sleep they got each night was 7.1 hours with a standard deviation of 0.78 hours. Assume the variables normally distributed. We've got that. We've got a small sample size, so we're going to construct a 95% confidence level for the population mean. So over here on the side, I'm just going to jot down a couple of things. So sample size, X bar, and S, right? Sample standard deviation. Notice that the data that I give you in this first sentence is all from the sample. So I don't know sigma. I know that S is 0.78. I know that the X bar, the average for these 10 students, was 7.1 hours, and I know that the survey was given to 10 students. The only other thing that we need to know is our T of alpha over 2. It's a 95% confidence level. So I'm going to go back to my T table, and I'm going to use degrees of freedom of 9, right? Because I always, and minus 1. So I believe when I do degree of freedom 9 and go across to 95% confidence level, I believe that gives me a critical value of 2.262. So then I can go ahead and do construct my confidence interval. So I've got mu in the middle. So I'm going to take my X bar minus, whoops, I should put a number in there, shouldn't I? A 7.1 minus my margin of error, and a 7.1 plus that margin of error. So that's going to be my T value, 2.262 times my standard deviation, 0.78, divided by the square root of my sample size, 10. Over here, it's going to be identical, 2.262, and my standard deviation, 0.78, divided by my square root of 10. So notice, remember, these two guys are the same thing. We've just got ourselves different places, so this is the same X bar plus and minus those two things. I'm going to go out to 2 decimal places. So I ended up with my mu value, my mean number of hours of sleep for dancers is somewhere between, I ended up with a 6.54 and a 7.66 hours. Now that's based on this very small sample, right? So my mean might end up in there if I found the true population mean, but I could be off because maybe I didn't have the best sample out there that I possibly could. Maybe that's high. Maybe you think that average number of hours of sleep, 7.1, is quite high. I don't know. But that's my final construction for that. So I hope you're nodding at me and saying this seems very much like what we did before. The only difference is the critical value using the T table instead of the Z table. Notice your critical value will change for every single problem because it's all dependent on those degrees of freedom. So you have to look it up every single time. There's not the repetition when we use the Z. If it's 95%, it's always this Z value. So I just want to point out this last problem. I don't think we need to do this, but it asks for the following data, construct a 95% confidence interval for the population mean. So I know that I'm going to do this. I know that I need the same things that I did before, my N, my X bar, my S, and I'm going to need my critical value at a 98%. Well, here's the thing. That last problem, I gave you everything. I do know N. I've got 1, 2, 3, 4, 5, 6, 7 pieces of data. I, however, do not have X bar and S, right? I can look up my T value. So to find these two, you are going to need to use your TI-84 and find your X bar and your sample standard deviation. Then you can complete that problem and construct your confidence interval. That is it for section 7.2. I hope this feels like a review, and I hope everybody's good with your T-table. Have a great one, and I will see you in section 7.3.